So we will continue from where we left off yesterday and make some progress in sulfuric acid. Won't finish it though. We started talking about this, that how sulfur is recovered from oil and natural gas by hydrotreating and then carrying out the Claus process. But what we said is that this process does not go to completion just by the simple thermal route. That's because the temperature at which this is being done is quite high, and because of that, the equilibrium really tends to shift a bit to the left, and so you don't have really the complete conversion of H2S and SO2 going to sulfur. So this is incomplete, and we also discussed yesterday that the best thing to do would be to try and reduce the temperature. For that, you need to have some kind of a catalyst which can hasten the reaction at a lower temperature. And we said that alumina and titania are some of the catalysts which have been found very suitable for this. So that's the sum and substance of the catalytic step. So the Claus process is done non-catalytically first, thermally, and then it is done in this catalytic manner. Before I again come to that, let me also tell you that whenever you do these reactions, one is of course, look out for whatever is your main product that you're looking for. That's important. Look at the conversion, etc. But you must also look at what are possible side products which might form, because they can form, and even if they're in small quantities, they can form. And sometimes it could be quite dangerous, or it could be problematic to separate them. Like for example, one of the side reactions, even though the delta H is positive and therefore not very favored, in that sense. Like for example, if you take H2S, it can just decompose into sulfur and hydrogen. Okay. Now, this is very risky if this happens. Can anyone tell me why?
Sir, hydrogen is combustible.
Yeah, and what is there to combust with it?
Sir, air.
Oxygen.
Yes, because we are using oxygen in this process. Obviously, H2 and O2 under high temperatures can form an explosive mixture. And so it would be very risky if this were to happen. So one has to take care to make sure that these kinds of reactions do not take place. Now, another reaction which can generate hydrogen is basically this reaction. Methane reacting with water forming CO2 plus 4H2. Can anyone tell me where methane might come from?
Natural gas.
Yes, because we are doing hydrotreating of natural gas. And so, along with the H2S, there's always some amount of methane that can get in. So that's important to know. Now, just as an aside, when you have this kind of CO2 forming, there is H2S around, okay, it can form things like carbonyl sulfide, or the methane can react with sulfur, which is formed, and can form carbon disulfide. So these are all side reactions that can take place. Now, let me also tell you, it's quite interesting, just like we talked about Bowler from ammonium cyanate when he got urea and was excited and said he made it without any dog or cat. So here also what happens is quite interesting, that in presence of chlorine, you can actually form from carbon disulfide, which is formed, you can react and form carbon tetrachloride. This can actually dimerize. That will give you trichloroacetic acid, and eventually from this you can get acetic acid. And this was actually achieved by Kolbe. So this was another very, very important organic molecule, which was made from purely inorganic substances. In many of our metabolism, and especially in plants, you form acetic acid. So this was another classic case. So it was not just Wohler, but Kolbe had also made something extremely important, an organic chemical from purely inorganic substances. So it's just as an aside, but it's an interesting thing to make a note of. Now, what happens is that when you carry out this catalytic step, there is an advantage of doing it at a lower temperature. That advantage being that the equilibrium will shift to the right, it being an exothermic reaction. But the problem is, although you are forming sulfur in a gaseous form, once you go to the lower temperatures, the sulfur can go below the dew point, and in which case it will form a liquid droplet around the catalyst, and it can poison the catalyst, it can deactivate the catalyst in the presence of the sulfur. Typically, what people have been doing is that operating it above the dew point so that this kind of liquid droplets do not settle on the catalyst. But what that does then is that the completion is then not 100%. And so people have strived to go below the dew point. But then, as I told you, there would be this problem of forming droplets and poisoning, deactivating the catalyst. Chemical engineers have always been very intelligent, very smart in circumventing such problems. What might you do if you try to do this below the dew point and it is done? But how would you resolve this apparent contradiction?
Sir, using a catalyst with a higher efficiency.
Yeah, efficiency, but you're constrained by the equilibrium. It's not the, that's not the issue. I mean, and in fact, the very fact that there is a way of operating below the dew point, means at a lower temperature, means that actually you are operating with a catalyst with a higher efficiency, with a low activation barrier. The issue is not that.
So, by increasing the pressure?
By increasing the pressure, you liquefy it even more. You can say by reducing the pressure. No?
Yes, sir, by reducing the pressure.
Yeah, you mean by reducing the pressure. Yeah, you could, except that what happens is that whenever you operate with a reduced pressure, that's a very good suggestion. But when you are doing this kind of a reaction, when you reduce the pressure, what will happen is that the residence time of the reactants with your catalyst will reduce. Because spending less time. It's getting swept away fast. And so it may not get enough of a contact time with the catalyst for the reaction. So while it's a good idea, the reduced residence time can create a problem when you are at negative pressure. You understood?
Yes, sir.
Okay. So again, there's a dilemma, but I think you did come up with a good idea. So I'll let you put that. Operate at reduced pressure. And the others, and another you said use catalyst of higher efficiency. And I'm putting these, but these don't mean that they're necessarily the right answers. Okay? But there are problems. But there are, you're thinking. That's very nice. Many times what you should do is that look for again simpler solutions which again don't get you into a discovery mode. Like if you want to search for another catalyst, there are issues. But then as I said, that's not the core issue. The core issue is that there are liquid droplets which can deactivate the catalyst. And if you try to apply a vacuum and lower the temperature, it's a good idea. But then what it will do is that it will reduce the contact time of the reactants with the catalyst, which is again could defeat the purpose. You need a minimum residence time. So what they've done is very smart. What they're doing is they actually have two catalyst beds, maybe more. I'm just illustrating it with two. And they still operate at the subdew point. Now, what they do is that When one catalyst bed gets deactivated because there's too much of sulfur that is deposited, they divert the flow to the second bed. And then the first bed is regenerated by heating it at high temperature and pushing off all the sulfur. And then they just keep going back and forth between the two reactors. So you can see, to avoid liquid sulfur physically deactivating the catalyst, process is operated above the sulfur dew point normally. Whereas greater conversion can be achieved at lower temperatures. The subsequent innovation is that the Claus process operates with reactors in parallel. When one reactor has become saturated with adsorbed sulfur, the process flow is diverted to the standby reactor. The reactor is then regenerated by sending hot process gas to vaporize the sulfur, which is then condensed. And like that, from a very difficult thing otherwise, they have been able to reach greater than 97% yield with respect to the input sulfur, in terms of H2S. The steam requirement is about 2.6 tons per ton of sulfur. This again gives you an idea, just like you saw in the crash process, how by using froth you can lift up the material. Here you can see that just taking two reactors in parallel, that you can solve a problem in a relatively practical way. So as engineers, always look for the most practical solution. It need not be the most hi-fi solution, but it must be practical, it must be cost effective. And it invariably, it's important to know that while the Claus process has been practiced for more than a century perhaps, but this process is a very complex process. It's a multi-electron process and is not so easy to figure out the detailed pathway and the mechanisms. You can see even in 2005, there's a very nice paper on fundamental studies of this process. Many times what will happen is that the research that people do or should be doing should actually generate the underpinning knowledge behind the products and processes that we produce. That would be actually the best thing to do. You should look around and ask yourself all the time, is everything known about what there is to know? Or can I know something more? That's how you generate ideas for research. Now, let's look at, as we go towards sulfuric acid, we've got the feedstock now. We've got sulfur. Or if you are working with iron pyrite, you might be able to generate SO2. So not necessarily starting from sulfur. So there are two ways of doing it. Okay. Now, what is important to know is that if I burn sulfur and make SO2, it's very exothermic. If I do the SO2 to SO3 conversion, this is the so-called contact process, it's exothermic again. I mean, not as exothermic as this, but nonetheless quite exothermic. SO3 absorption into water to make sulfuric acid is also highly exothermic. So all of these are exothermic reactions. Okay. What does it tell you about the state of sulfur? What kind of a substance is sulfur?
It is unstable, sir, and it wants to get oxidized to become stable.
Right. So it is a high energy material. And that's why you have so many fireworks, explosives, etc., matchstick, where you use sulfur. Why do you use it? Because sulfur is an energetic material. And what's the proof of it? That everything that you do with it, it basically releases enormous amounts of heat. So you know that therefore sulfur is an unstable material. Just bear that in mind. Obviously, like for example, where there are sulfur mines, there must have been some kind of a process which made such an high energy material available, and it could be that it was under anaerobic conditions and there was large amounts of energy that was supplied. Just like you saw, H2S can decompose and form sulfur and hydrogen, which would be possible if it was a completely anaerobic condition. So for example, underground, if your conditions are anaerobic, like, you have a volcano or something, there can be extremely high temperatures that are generated. So under those conditions, you might be able to produce sulfur because there is no oxygen to react with. So just keep such things in mind. It's always very interesting to ask, okay, if it is unstable, then how did it form? Why should it form? And that's the way it will form. There must be an energy input from somewhere to push it up to that energy. And also there must be favorable conditions, like in this particular case, it's an anaerobic condition. Now, let us look a little more deeply at the equilibrium composition of SO2, SO3 and O2 as a function of temperature. It's important because after all, what are you doing? You're first really taking SO2 in the contact process and you're forming SO3. Now, this study was done taking a 3O2 to S2 ratio. Means it's basically taking the SO3 that if required, I can form all SO3. So I've given it that much of a oxygen ratio, 3O2 S2. If all of it is not SO3, then what will happen? There will be some SO2 and some O2. That's what will happen. Yeah. Now, what you can see is that when you go below around 600, maybe 650 or 600 thereabouts, you find that you can completely, provided I'm giving all the time and effort to convert it into SO3, okay, catalyst, that, whatever, but thermodynamically it would completely exist as SO3, okay, provided the temperature is below around 600 K. But when I go to higher temperatures, you can see what is happening is that the SO3 mole fraction is reducing. So it's becoming, say, 0.6. Now, when my SO3 mole fraction is reducing, then what will happen is that some amount of it must be, of the sulfur must be present as SO2. Okay. So that's precisely what happens. That's what these curves are telling you, that the equilibrium constant becomes increasingly unfavorable, okay, at a higher temperature for formation of SO3, and therefore I will have SO2 left over. Now, what it also means is that if I am doing the contact process, and I'm trying to form SO3 from SO2, then make a note of what would be the favorable temperature at which I will get quantitative formation of SO3. So your catalyst must be tuned to this kind of a temperature range. Now, you can also look at the extremity, that when you are at something like 1400 K or let's say about 1125 degree Celsius, typically like the temperatures in a thermal power plant, where when a combustion of coal is taking place, subsequent temperatures reduce, but it is very high, the temperature. So what happens is that the sulfur, the SOx that is liberated from coal power plants, etc., typically tends to be SO2, not SO3. And that's just because of the temperature range at which the process is taking place. So in some ways, these are very, very important things to make a note of. There's a company for which I consult. These people actually roast catalysts, spent catalysts. So they try to recover metals and things like that from the catalyst. These catalysts are basically go dead. They are hydrotreating catalysts when there is a huge amount of deposition of sulfur compounds, etc. And then at that point, the refineries go for a fresh lot of catalyst and chuck this away, sell it to these kinds of companies, and those companies regenerate the metal, nickel, vanadium, molybdenum, etc. from these catalysts. Now, in their case, what happens is that their roasting temperature is around maybe around 600, 700 degree Celsius or thereabout. So it's somewhere here, somewhere here. Okay. So it was an interesting situation, where there is SO2 and SO3 being formed. They were looking for some kind of a cost-effective solution to reduce the scrubbing cost. A patent was granted to us just this year on this. I'll come back to it and tell you exactly what was the invention that got granted a patent this year. Is this plot clear to everybody? Have you understood the basics?
Yes, sir.
Okay. Let's again look at things which I'm sure all of you are very familiar with. Again, we are looking at this reaction 2SO2 plus O2 going to 2SO3. I've given the delta G, delta H, and delta S values. Now, let me also tell you that these values don't fall from the sky. It actually comes from studies like this, from which you get the equilibrium constant. From that, you will be able to generate delta G. From the effects of temperature, you'll be able to say something about delta H. That's how you generate some of these results, these numbers. Okay? These numbers don't just come like that. They come from those kinds of studies. All right. So you've got an idea. All right. So delta G for this is negative. So obviously the free energy is favorable at a temperature of 25 degrees centigrade. Temperature is important. At what temperature? We are talking about delta G at what temperature. We also know that the equilibrium constant is related to the temperature, and this is the relationship, okay, the Van't equation. So if, for example, if I am operating at a certain temperature, and I know the value of delta H at that temperature, and I know the value of K from the delta G, let's say, I would be able to calculate the K at another temperature, and accordingly I'll be getting the delta G at that temperature from minus RTLN K. So this is an important equation. Keep that in mind. I'm sure you already know it. Now let's look at an exothermic reaction, because that's what it is, an exothermic reaction. The SO2 going to SO3, you can see the delta H value. It's not very different from this plot, right? At a certain temperature, you'll get a 100% conversion. Suppose I were to carry out the reaction isothermally at the temperature, where my conversion is close to 100%. I can do that, but that means that if it is isothermal, then I really have to carry out the reaction under a reversible condition, and I have to continuously remove the heat that is being generated, so that the temperature does not rise, and so I maintain isothermal conditions. Practically, it's difficult to do. It's okay to do an experiment in the laboratory, but otherwise it's not so straightforward, and also it may not be that sensible, even if I could do it. I'll tell you why it may not be so sensible. Let's look at the other extreme, that I don't remove the heat at all. And so what am I doing? I am operating under adiabatic condition. Obviously then my temperature has to rise as the reaction is taking place. The moment my temperature rises, my conversion will fall from the equilibrium conversion curve. So I have a problem if I try to do it adiabatically, strictly adiabatically. Chemical engineers always look for a smart way out. You saw like what they also did with the subdue temperature process, smart solution. Just have two catalytic beds in parallel. So similarly, here, what they do is that they operate in a domain which you can call as intermediate between isothermal and adiabatic. So that I may not get what is so extraordinary, that isothermal theoretical conversion, but I'll get a decent conversion. And if I can do it in a smart way, as is done in the contact process, I can actually pretty much achieve the the conversion for an isothermal process without it being an isothermal process. Yeah, that's smartness. That's what engineers are so good at. So what we will be doing is that when we discuss the process, we'll have to keep that in mind. Second thing that you have to keep in mind is that what is the catalyst that is used in the contact process? Do you know?
Vanadium pentoxide.
Wow,
205.
you know that. Vanadium pentoxide. Now, one thing obviously will be apparent is that the catalyst must be able to operate at the temperature range where it would be in sync with the kind of conversions that I am expecting to get. Because if I don't, if my catalyst is only active at 1000 degrees centigrade, doesn't help me. That also sets the research in motion, that if you are looking for a catalyst, it's not good enough to say, hey, I found a catalyst for SO2 to SO3. You have to ask, at what temperature does it operate? What is the activation barrier? We are not going to jump into the to the contact process. Let us first see what was the process that preceded the contact process and preceded by a long margin of time. And believe me, it was a good enough process that it was practiced, in fact, even in 1946 and thereabouts, long after the contact process had been operational, and about 25% of the production was still by that other process, which I will now describe to you. Who was the person who discovered that process? Well, none other than John Glauber. In the 17th century, when Glauber was working, Glauber was considered to be the greatest chemist. There was no chemist more famous than Glauber, and all this stuff that you have learnt in your probably in your high school laboratory, that if I take some compound and I add sulfuric acid, and I can liberate HCl or gases of nitric oxide, and from that I can say what is there in my compound, right? That is the kind of qualitative test that we have learned. It's all due to Glauber. Glauber is the one who had taught us this, and probably because of this test, I don't know or why, but Glauber had a deep interest in sulfuric acid, and Glauber was the one who first developed a process for making sulfuric acid in the 17th century. What did Glauber do? Why he did this experiment, don't ask me, because I have not seen the record. And maybe if you go back to his original papers, or if in case he published anything, I don't know. But what he did was that he was burning sulfur. It's possible that he knew that saltpeter is basically potassium nitrate, and nitrate is an oxidizing agent. By the way, I'm just guessing. I have no idea whether it is wrong or not. Maybe they were trying to make explosives, and sulfur is a fuel and potassium nitrate is a oxidant. I've got a fuel and an oxidizer. That's what I require to make explosives. The Chinese had made explosives. They were probably the first ones to have done it. Who knows? He might have wanted to make an explosive using a fuel and a oxidizing agent. But what happened was that in the presence of the saltpeter, this formed sulfuric acid very efficiently. And then in 1746, long after Glauber's work, we have been about 70-80 years later, John Roebuck, probably a Britisher, he actually developed a process for actually commercially producing sulfuric acid. At that time, what happened was that, when probably Glauber and others after him were producing this stuff, they were using glass containers. Now, how big a glass container can you use? It's only small amounts of substance that you can produce. Of course, maybe in tune with the pre-industrial revolution era. when people produced things in their home. So I could have produced a few kilograms of sulfuric acid this way. But Roebuck basically replaced the glass containers with lead-lined chambers. It's also interesting why he chose lead. Probably they had the skill of making lead chambers, big, massive reactors out of lead. Lead was a common metal to use. Another reason could have been, although I'm not very sure, lead was also quite cheap. Okay, lead was not a costly metal. And also, those were not the days when you had steel and those furnaces, etc. Steel furnace and those things came much later. Lead was easier to handle. Do you see any other possible reason for lead?
Sir, it's non-reactive. as in
Non-reactive
with the
to-
reaction, with the particular reaction concerned.
I think you got the answer, not very crisply. Can you be a bit more
So
precise?
lead sulfate would
Brilliant,
make a
brilliant,
thin layer.
brilliant. Very nice. Between the two of you, you have cracked it. And mind you, we are just speculating. I've not seen it written anywhere. Why lead? Maybe technology existed to produce such reactors. Lead was not too costly.
So it is also very malleable, so you can shape it in whatever shape.
Malleable. Yes, and especially lead. Lead is what people used in the printing press to make all the letters in the first printing presses.
Even water pipes,
Water
usually
pipes.
pipes.
Yes. And also not a very high temperature of processing. Malleable forms passivating layer with sulfuric acid because of lead sulfate. Any other reason why lead instead of glass? Could there have been other advantages?
So more temperature resistance.
Let's put it down.
So like if you used to use glass and if you increase and decrease the temperature in an instant, it would crack. This wouldn't happen with any metal as such easily.
Yeah, so you have, wait. Some link drawn with temperature. I mean, you have brought temperature into the picture. Think about the reaction which you're trying to do. What would lead have an advantage over glass? What was the reaction that you're trying to do? What are you trying to make?
Sulfuric
Sulfuric
acid.
acid.
What did we say about what happens when you burn sulfur? It releases a lot of heat, right?
Yes, sir.
Right. And so if it releases heat, I need to actually remove heat.
So it is a conducting layer. So
Right. Thermal conductivity. Okay.
Yes, sir.
I want to dissipate the heat. Can dissipate heat more efficiently. Imagine how boring these lectures would be if we just said, take a lead vessel, carry out the reaction and this, that. And moment you start asking questions like why, everything comes alive. And things are not so dull. All clear?
Yes, sir.
Yes, sir.
Okay. Now, so you can see that in the 17th century, Glauber discovered this reaction. 1746, John Roebuck used lead-lined chambers and was able to produce it on larger scale. And more or less the same technology that Roebuck practiced, or not just Roebuck, there were other people. We'll talk about their roles. And you can see, so robust was the process that as late as 1946, the chamber process still accounted for 25% of sulfuric acid manufactured. Have you any of you heard of the chamber process before?
Yes, sir.
In 12th.
Only the name.
Only the name. Okay. The point is that we don't do justice to these other people who did great things. In fact, when I start looking at the contact process and when I look at this, I mean, that's an incremental development. 1600 and something, Glover probably did his work. 1746, John Roebuck came up with this. Much later, almost about 60 years later, these two people, probably French people, came up with a mechanism. These were some of the earliest examples of someone actually asking the question, how does it work? What happens to the nitric acid? And they could make out that obviously Glover did not add stoichiometric quantity of chili saltpeter. Took some amount, but all the sulfuric acid was formed, all the sulfur got consumed, and it formed sulfuric acid. So obviously there was some kind of a notion of catalysis, but the concept, the term catalysis had not been born. But actually, let me tell you, many times the names are not known, okay, but people do equally great things, except that they're not smart enough to coin the term, or they're not smart enough to see a larger pattern. But they are the ones on whose shoulders other people rest. Now, so what these two people said is they proposed this reaction, and you will see how important this reaction mechanism was. The process of manufacture and the mechanism went hand in hand. So what did they say? That chili saltpeter decomposes to form NO2. NO2 has a oxidation state of +4, right? Nitrogen, right? And it disproportionates. And look at how many places we have encountered disproportionation, reproportionation chemistry. Everywhere. It was one of the most beautiful processes known in chemistry, of how the same thing can exist in two oxidation states, or things in two oxidation states can reform into one oxidation state. So over here it was disproportionating to HNO2 and HNO3, +3 and +5. So average will be 4. Nitric acid is a very powerful oxidizing agent. So they said nitric acid is reacting with the SO2. So burning of S to form SO2 happens. There's no problem in that reaction. The problem comes in the second reaction, which is the SO2 basically becoming SO3. SO2 then gets oxidized, but it's very interesting. It is not SO3 and some reduced form of nitric oxide, like nitrous oxide being formed. What they said is that it forms an intermediate NOHSO4, nitrosyl sulfate. And they actually called it as the rational explanation based on an intermediate compound theory. That's what they called it. Intermediate compound theory. This is the intermediate compound. Now, this intermediate compound had a very interesting property. If you have water in it, you put water, it decomposes and forms sulfuric acid, and now it goes to NO2. So from the +5 oxidation state, it's gone back to +4 oxidizing state, and it forms NO. So that's what happened. And in the process, your SO2 basically got converted into SO3, which is how you ended up getting sulfuric acid. What they then said is, you see, NO2 is reacting with this and I'm getting this. But the problem is that if I form NO, and every time this reaction, I'll get more and more NO. So finally I'll use up all my chili saltpeter, right? So I need to oxidize my NO back to NO2. That is the rate determining step of this process. And it is rate determining, no doubt, and delta H is, you can see the value of this. But this step is far more facile than the oxidation of SO2 to SO3 by oxygen. SO2 also can react with HNO2 and it can form H2SO4 plus NO. So that's another parallel reaction that takes place. But all of these basically ended up producing NO. So what happened was that unless I can regenerate NO2 from my NO, my thing will go dead. And so this chamber process is not about the oxidation of SO2 by oxygen to SO3, but it is about the indirect oxidation of SO2 to SO3 via NO2. And NO2 is really what is getting oxidized in the chamber process. And the net, of course, reaction I can write as 2SO2 plus 2H2O plus O2 going to 2H2SO4. Very interestingly, you can see it's a catalytic reaction, but no one had called it a catalyst. They didn't even know what is a catalyst at that point. But today we, of course, know it as a catalytic reaction. So we will continue with this on Monday.